Good afternoon and welcome to the College of Optical Sciences Colloquium series. We have a very full room today. It's standing room only, or close enough to it that people are standing. Today we're very fortunate to have Professor Eli Yablonovich from University of California, Berkeley with us to give us a talk on efficiency in solar cells. Professor Yablonovich is the director of the National Science Foundation's Center for Energy Efficient Electronics Science, or E3S, which is a multi-university center based at Berkeley. He received his doctorate degree in applied physics from Harvard in 1972. And in his photovoltaic research, he introduced the 4n squared light trapping factor that is in worldwide use for almost all commercial solar panels. This factor increased the theoretical limits and practical efficiency of solar cells. And the 4n squared is based on statistical mechanics and is sometimes called the Yablonovich limit. Dean Koch arranged for Professor Yablonovich to be with us today, and unfortunately Tom's out of town, but we're very fortunate to have him, and I'll let you...
Okay, thank you very much for the introduction. What I suggest is that someone should be delegated to explain all this to the dean when he gets back. Okay, so this is actually one of my favorite topics. The solar cell field is in a tremendous roller coaster of production and efficiency, and so there's a lot's been going on, but it's something in the energy field. Energy business goes up and down. It's cyclical, like many commodities, but the science marches forward. So I will talk about the science of solar cells, and I'll try to explain the solar cells in a way probably you've never heard it explained before, in sort of a very fundamental way. And so let me get started by describing everyone has seen this, the solar panels. You go around Arizona, you'll see some solar panels here in Arizona, but if you want to really see a lot of solar panels, go to Germany. They have subsidized the tremendous installation of solar panels. It's just all over Germany, vast areas. It's quite surprising. Now, if you look at the volume of production, it's somewhat historical in the change that has occurred in the past 5 years. And actually, I entered this field much earlier than 2000. I entered this field in 1980, when it was a very tiny industry, and maybe a few tens of megawatts of panels were being created. And you can see what has happened now is that the panel production is measured in gigawatts, and each watt costs about $1. So you can see what has happened. The industry has grown tremendously. I believe this year it's going to be close to 30 gigawatts of new panels being installed. And that's like $30 billion, not counting the installation cost. So it's a very, very big change in society. If you look at this kind of growth, it really gives new meaning to the word exponential. Indeed, the compound annual growth rate is 46%. And I can tell you, I would love to have a company that grows at a 46% compound annual growth rate. But that's not just for 1 year, but this is for 15 years. So it's really been going on. Now, you might think, well, it's the same old solar panel, but there have been some distinct improvements over the years. This graph only goes back to 1985. If you go back to 1980, the price was $10 a watt. But in today's dollars, it was like $30 a watt. And you go down and you see the price has been steadily dropping over the past 30 years. There was a little blip a few years ago where the price went up. There was an actual silicon shortage briefly, and the price went up, but the silicon shortage is over, and now the price is coming down. It's down below the trend line, and actually it's well below $1 a watt, which is rather amazing. Now, the cumulative install worldwide is also very substantial. It is believed that cumulatively all over the world, 70 gigawatts have been installed. And just remember that each gigawatt is like a nuclear power plant. At least at the peak of the day, it would produce as much energy as a nuclear power plant. So it's like 70 nuclear power plants worth of cumulative install today. So that's rather remarkable. Now, the country that has done the most on this is Germany. And this is a graph of the daily use of energy, production of electricity in Germany. And by some coincidence, I've chosen to do this in the month of May. Now, the reason I've done this in the month of May is that you say, well, what is the sunniest month? Is June. But solar cells are little thermodynamic engines, and they run better when they're cool. So you actually get more electricity in May than in June. You get a lot of sun, but it's a little bit cooler. And so you actually get more electricity. So this was the end of May, and this was the national energy production of Germany. And you can see that a very significant percentage was already coming from solar. And in fact, if you include wind, which was a little tiny blip by comparison, about half the electricity in Germany at noon on a Saturday. So why at noon? At noon because you have the most sun. Why on a Saturday? Because you don't use as much electricity, so the solar panels look disproportionately large. They are disproportionately large. And under those conditions, on May 26th of this year, the solar electricity was close to 1/2 of all the electricity in Germany. Now, why is this? Well, the reason is sociological. There were tremendous subsidies in Germany. To give you an example of how strong the subsidies were, they were offering to pay 59 euro cents per kilowatt hour. Now, probably you're not calibrated at your own bill, but the typical bill around here would be maybe 10, 12 cents a kilowatt hour. They were offering 59 euro cents. Obviously, a tremendous subsidy. The vast arrays of solar panels were built in Germany, and at least they got something from it. Is that on a weekend Saturday in May, they were half the electricity was coming from solar panels. So that's rather remarkable. Now, what is the degree of improvement? Now, some people say, well, the improvement, it's there's a learning curve. Any product, if you produce more of it, you'll become more efficient at doing it. And that's true, but the increased efficiency it's not automatic. The increased efficiency arises because engineers and scientists come up with improvements. Okay, and there have been tangible improvements. And if I go back to when I started in the field, actually in 1980, I go back and the price then, I remember it very well, was $10 a watt. And but those are real dollars. Those were 1980 dollars. It is now closer to $1 a watt, and this cumulative installed has now risen. This is a year old, so I've got to change all the numbers. It's now risen to 70 gigawatts cumulative installed. And the price is now well below $1. But let me talk about the price drop over the past 30 years. It's a factor of 10 in price. It went from $10 to $1. But it's actually more than that, because when you take inflation into account, it actually, the cost has gone down by a factor of 30. And I can point to specific technological improvements, say, that has resulted in the cost going down. So it wasn't automatic. You needed science. You needed clever engineering ideas and so forth. The cost has really come down. Now, the projection about a year ago was that there would be, and what is a factor 30 over 30 years is roughly a factor 3 in real tangible price reduction every 10 years. So the projection is over the next 10 years, there's going to be another factor 3. And then the price of the panels will be down to 33 cents. And at 33 cents a watt, that would become the cheapest form of primary energy, period. So that's what's projected. But instead, what has happened is due to the tremendous production subsidies in China, there's a price war has broken out. And now the solar panels, well, no one wants to admit how low the price is. There are rumors of a price of 40 cents a watt. So what would have required 10 years of technical progress seems to have occurred in 1 year as a result of over-subsidy in China, excess production subsidies. But in any case, there is the hope that in the next 5 years, the subsidies will not be needed. And there is a projection, I don't know if this will happen, but it seems likely to happen, that there will be 1 terawatt of solar panels installed by 2020. So it's quite something. So it's very interesting to talk about this science because it is a science that has a scientific aspect but also has a social aspect. And the social aspect has to do with the importance of efficiency. This is more of an economic aspect. We'll get to the social aspect in due course. But if you look at the cost of the electricity, you have to pay for a bunch of things. You have to pay for the glass, the installation, and so forth. And all of that stuff, all those costs have efficiency in the denominator. And because the efficiency is in the denominator, there's a tremendous motivation to increase the efficiency. If you increase the efficiency, the cost will come down. And I don't think that's terribly controversial. I got this slide from Professor Barnett from the University of Delaware. And he shows the 40% efficient solar panels would be the least expensive. However, it's a very controversial point. And this is more of a social thing in that I have here, I downloaded, this is a little out of date, the stock market from Yahoo Finance, the stock market valuation of one of the more important solar companies in the United States called First Solar. And they make cadmium telluride cells, and they're not so efficient. And nonetheless, the market capitalization, I think even today, is about $2 billion. So that company that makes very inefficient panels is recognized by the stock market as being worth $2 billion. Whereas another company, which I do respect them more, because they have higher efficiency. And they have a lot of science. Their cells are very, very ingenious. And they have boosted the efficiency. Well, they claim now 24% in production, which is phenomenal. The record is 25. And so that's rather remarkable. So you think, and I know the founder, and I know he's one of the most brilliant people I've met. And nonetheless, the stock market has actually devalued the company. When I took the screenshot, it was 800 million. It's now down to closer to 500 million. So there's much more respect given to the low efficiency company than the high efficiency company. This is very strange. So it's one of those odd things. And I don't agree with the stock market. And maybe it means I should buy one and sell the other one short. But I've got other fish to fry. Okay, so that shows you it's controversial. Not everybody agrees that efficiency is important. Some people think just the lowest cost of the panel. But to make a really low-cost panel, efficiency is critical. So I will do this partly as a little bit of a tutorial. Just try to answer a few questions about solar cells. So first of all, why is the p-n junction merely optional? So maybe somebody has told you that solar cells, the key to a solar cell is the p-n junction. And I will say, no. It's optional. That's not the key to the solar cell. And then it's easy to calculate the current of a solar cell because you need to be a bookkeeper. You just say, well, where do the photons go? Count up the current. So everybody understands the current, but the voltage is much more difficult to understand. So I will explain where the voltage comes from. What determines the voltage of a solar cell? And then it turns out that the optics, and this is why I'm here at the Optical Sciences Center, the optics inside a solar cell is actually very important. And we need to use statistical mechanics to analyze the optics inside a solar cell. And we're going to do that. And then I'll answer a question which people always ask me. They always say, are photonic crystals of any help towards solar cells? And I used to say no. But now I've sort of mellowed a little bit. And yes, probably there are certain types of very thin solar cells, the photonic crystals probably would be helpful. And we'll see. And then we'll get more to the economic, sociological things. What are the top competing technologies, and what is the status of the industry today? So this is what I'm going to cover. Now, let me answer first, what is a solar cell? I would like you to forget anything anyone else told you, because I'm going to tell it to you a little differently. Think of a solar cell as being a container, and in this case, it's a rectangular container. And this container, maybe it's made of silicon, and so it captures photons. The photons go into the silicon, and they produce electrons and holes. And the goal in a solar cell is to build up a very, very high density of electrons and holes. Now, what could stand in the way is that the surface of silicon, like most semiconductors, has many dangling bonds. The dangling bonds are like defects, and the electrons and holes will recombine and prevent you from building up a high density. So to eliminate the problem of the surface recombination, you coat the surface with a wider bandgap material so that the electrons and holes can never see the exterior surface. Now, if this is silicon, then the normal wider bandgap material that you would use is silicon dioxide. And silicon dioxide has remarkable properties. It coats the silicon and almost perfectly eliminates all the dangling bonds. So now I have the container I wanted for the electrons and holes. Now, what makes it a solar cell? Well, I attach a wire, and in semiconductors, the metallurgy of connecting up wires is quite remarkable. In fact, it's quite common to have a wire that makes electrical contact only to electrons, and another wire that makes electrical contact only to holes. So I have built up this gas, this high-density gas of electrons and holes, and I'm going to switch over to the left side here, and you see that there's a great truth about semiconductors. The electrons and holes, they live in different worlds. They hardly ever recombine. They ignore each other, and each one has its own Fermi level. Okay, and a Fermi level means that they are coexisting in the same volume of space. You have two different Fermi levels. Don't tell this to anyone from the physics department. They will get upset. Okay, but in electrical engineering, it's okay. We're accustomed to having two Fermi levels. Okay, and now if you make electrical contact to the electrons, you get one Fermi level. To the holes, you get a different Fermi level. And so you get out a voltage. And so you're making electrical contact here, and you get out a voltage that corresponds to whatever separation there was between the Fermi levels. Now, if you know a little bit about semiconductors, the more electrons and holes you have, the wider this separation in quasi-Fermi levels. Okay? So this becomes then, it's the selective contacts. You try to build up an electron-hole gas, and you make a contact to the electrons, a separate contact to the holes, and you get out electricity. Okay? So notice that I never mention anything about a p-n junction. Okay? So I say the p-n junction is optional. And you'll see that in a minute. Now you say, the trick must be those selective contacts. There's some sneaky trick with the selective contacts. There are many ways to make selective contacts. Let me show you a couple of ways. Let's say you had a heterostructure, which is very common. So you have something with a bigger band gap, and the change in band gap all occurs in the conduction band. So if you have electrons here, they get reflected. The electrons get reflected because there's this big barrier. On the other hand, the holes go straight through. Now you have a selective contact to holes. Likewise, you could have it the other way around, where the electrons go straight through and the holes just get turned around. Okay? So this is one. There are actually, if you speak to a metallurgist, there are actually many, many ways of making a selective contact. This is just one of the ways. So selective contacts do exist, and it's not a problem. Okay, so that's it. A solar cell does not require a p-n junction. So let me give you a better model for the solar cell. And this is the bucket model, if you like. And just imagine you have a bucket out in the rain, and the raindrops are like photons. So the raindrops are falling in the bucket. And you're going to use this bucket to create mechanical work. And you're going to have a faucet. You're going to build up some pressure. You'll have a faucet here. You'll open the faucet. The water will come streaming out and will turn a water wheel, and you'll get mechanical work. So you're out there. You're trying to get mechanical work out of the rainfall. Now, what's working against you? Well, if the water leaks out the bottom, that's similar to bulk recombination in a semiconductor. So this is the analogy to a solar cell. If it leaks out the side, that's like surface recombination. Now, the recombination is very important because you need to build up a big pressure head. You don't want it just to have water. You want to have water coming out with a certain amount of pressure. So the water flow is like current, and the pressure is like voltage. And so this is the analogy, current times voltage. That's your solar cell output power. So I will go a step further with that model. But first I'll let you know what's coming. The key things about a solar cell are listed here: the fill factor, the current, and the voltage. Okay, and I'll explain each of these, and then we'll be almost done. Okay, what about this fill factor concept? So you have an issue. Let's say you have this water bucket model. The rain is falling in, but you have opened the faucet wide open. And if you open the faucet wide open, yes, a lot of water will come through, but the pressure will be very low. So you're not going to get much work done. So you can go to the other extreme. Raindrops are coming in, and you keep the faucet very, very tight, not completely, just a few drops come through. And yes, you've built up a tremendous pressure head, but there's almost no current. So if you're going to do this, you have to find an intermediate condition. You have to make a compromise. Not the full amount of current, not the full amount of pressure, the best balance where we maximize the current times the pressure. And so we have to find that optimal condition. We have a good amount of pressure, but we also have a good amount of current, and then we get the maximum power out. So this is completely analogous to finding the optimum condition for getting the power out of a solar cell. And you could be too greedy and get too much voltage. Then you'll get no current. So let me show you an example from these IV curves. This is basically the IV curve of a PN junction, except it's shifted down because you're injecting sunlight in. And in this third or fourth quadrant of the IV curve, you're actually producing electricity, which is fine. You say, well, I want to have a big voltage. So, wait a minute, if I have a big voltage, I have no current. Or I want to have a big current. Well, if I get the maximum current, I have no voltage. Now, in your fantasy, you say, well, I'll get the best of both worlds. And you get the power corresponding to the big rectangle. But you can't do that. You have to compromise, just like in the water bucket model. And so you have to have this compromise where you give up a little bit of pressure, but you keep your flow up. And so what you actually end up getting is a smaller rectangle, which is the actual optimum operating point where you've done the compromise. And so the ratio of these two rectangles, the small rectangle divided by the big rectangle, is called a fill factor. And it's usually pretty good. In some cases, it's 80%. The ideal fill factor is about 89%. And say, oh, well, this just has to do with the current voltage characteristics. It's just one of those things. But it's not. It's actually very fundamental. It's actually rooted in thermodynamics. It's not just something to do with the IV curve. And let me try to explain it this way. In thermodynamics, if you get greedy and you want all of one thing, that could be very improbable. Or you might say, oh, I want all of the other thing. Statistical mechanics, that's just a very, very improbable situation. So what you want to do is you want to have this compromise. And this particular compromise where you give up a little bit of what you thought might be possible to get, you get realistic, and it's actually the direct result of statistical mechanics, that you cannot get the maximum current and still have the maximum power. You have to compromise. Likewise, especially the voltage, you have to give up a few kT of voltage. kT is 25 millivolts, so you have to give some factor up in order to reach the thermodynamic optimum. So, but most of the time it's just described as being something to do with the IV curve, but it's really more fundamental. Okay, so that's about all I want to say about fill factor. It's not that big a deal. The theoretical limit is 89. I'm going to show you that people make cells with 86%, so you get close to the ideal. Do not try to exceed this, because if you exceed this, you're kidding yourself. You're going to end up violating statistical mechanical rules. Okay, so let me go on to the next thing in solar cells. We have the fill factor, the current, and the voltage. We've done the fill factor. Let's do the current. Obviously, you want to absorb as much of the incoming light in as thin a layer as possible. Equally, obviously, it's better to do this with a direct bandgap material rather than an indirect bandgap material. Well, you know that today, almost all this 25 gigawatts of production is crystalline silicon, which is indirect, but nonetheless, people live with it. But we'd rather have a direct bandgap if we could. Now, what happens when the light enters the solar cell? So I'm going to show you that at every important point, optics is the most critical thing in solar cells. It's not about the electrons and holes if you're talking about a good solar cell. It's all about the optics. So now we're going to analyze the optics of absorbing the light. Now, you might say, well, I have a plane parallel slab. The light ray comes in. It refracts again. And that's it. It just has a single pass. And that's how people made solar panels up until about 15 years ago. Then it was realized that, wait a minute, if you come in with light, all you have to do is, instead of having a plane parallel film or plane parallel slab, all you have to do is texture, put a little bit of texture. In this case, I put texture on both sides of the solar film. Even one side is enough. Now, the light ray comes in, it refracts, and then it finds a part of the silicon that's at some odd angle. It reflects at some strange angle, and then finds another piece of silicon at some strange angle. It reflects further at some strange angle. And after 2 or 3 reflections, it doesn't remember the original angle it had, and it's randomly scattering around inside the semiconductor. Now, you say, oh, well, that's kind of interesting. How big is the effect? Well, it's huge. And the reason is that this escape cone for the light inside a semiconductor, that escape cone is very, very narrow, perhaps only 15 degrees, and represents a very small part of the solid angle. And what happens then is that the light bounces around interminably, maybe 25 or 50 times internally, before it finally escapes. So you have, by simply texturing the surface of the solar cell, you have increased the internal path length for absorption by a factor 50. And that factor 50, if you do the trigonometry right and so on, that factor 50 is coming from 4 times refractive index squared. And, well, you say, oh, that looks like it might be of order of magnitude unity, because its refractive index can't be that big. Well, in a semiconductor, the refractive index is 3.5, and you square that as 12. You multiply by 4, it's 50, 48 or 50. So it's a huge effect. So that is very interesting, and leads then to a comparison between the solar cell and light-emitting diode. These are reciprocal devices. The solar cell takes in light, produces electricity, and the light-emitting diode takes in electricity and produces light. And we have this problem of the escape cone. That same problem occurs in light-emitting diodes. Let's say it wants to emit light, and in the escape cone it emits and it escapes. However, 98%, there's only 2% of the light is able to escape. 98% of the light is trapped, is beyond that 15-degree angle, and so is trapped and reflects and reflects and reflects and never gets out. Just goes on interminably. And also about 15 years ago, they used to make LEDs this way, when LEDs were inefficient. And they would typically get a 2% efficiency, and that was good enough back then. And of course, they don't do it anymore. Just as in the solar cells, we do the texturing, we do the same texturing now in light-emitting diodes. And what it means, yes, the light bounces around, but at least eventually, it has at least a probability of escaping. And if you have very low parasitic losses, you can make a very efficient LED. LEDs now are way over 50% efficient, and the reason is they're breaking the plane parallel symmetry. They're introducing some geometrical shape that lets the light escape. So this gets us into the area of geometry, of geometrical shapes. And so I'm going to teach something in this slide that goes back to kindergarten. So in kindergarten, you're supposed to learn about shapes. But there are different categories of shapes, and some of them behave very differently from others. And now imagine you have a light ray hitting a sphere. That light ray will refract, but it'll then refract right back out again. So that light ray will not be able to explore all internal angles, and it will actually not get trapped. It'll go straight through. I already said a rectangle, the light goes straight through. You don't get the benefit of the light trapping. A parallelogram is just like a rectangle. Now, this is what they don't teach in kindergarten, the word ergodic. Okay. Now, ergodic, I remember taking statistical mechanics, And it was all about being ergodic. And I said, well, thank God I don't have to take that class again. And I'll probably never have to use the word ergodic. So what does ergodic mean? It means that averaged over time is the same as averaging over all possible, it's over the phase space. So for us, the phase space is averaging over all possible internal angles. So obviously, over time, you do not access all the internal angles with any of these shapes. So unfortunately, these are bad shapes for LEDs. They're bad for solar cells. On the other hand, you're still in kindergarten. You might learn about some other shapes. And these are shapes that do trap light and that are ergodic. So for example, unlike the sphere, if you have an ellipsoid, actually it does randomize the light direction so that it is ergodic. You will eventually explore the full internal phase space. You'll get all the internal angles. The light will get trapped. It'll be you'll have a much more efficient solar cell and a much more efficient LED. Likewise, the trapezoid is good. So parallelogram is bad. Trapezoid is good. So it gives you some idea of what's going on. So the shapes you learned about in kindergarten are actually very, very important for solar cells. And we want to make our solar cells with some odd shape, not some plain parallel shape. Now, then you calculate, well, where does 4n squared come from? Light, I said it follows statistical mechanics, so it means you have to know the density of states. If you look at the mode density in a material with high refractive index, this is just a Planck law. You pick up a refractive index squared in a material with a refractive index. And so you get, obviously, more light just by the Planck radiation formula. And then there's a factor of 2 from double pass. And there's another factor of 2 from cosine theta averaging because the light is refracted almost normal. So you don't get the cosine theta averaging. But once it scatters internally, it has all odd angles, and the odd angles go over longer path lengths. So you pick up another factor, too. And that's where the factor 4n squared comes from. And it is a factor 50, and it is very valuable. So what can we say about it? Well, obviously, if it's 50 times more absorbing, you could make your solar cell 50 times thinner. And if it's expensive material, you can save a lot on cost. So that's one obvious benefit of this light trapping. A less obvious benefit, if it's a thinner cell, you make it thinner, you still absorb the light. There's maybe less series resistance. That has some effect, and it does lead to better fill factor. But less obviously, it also increases the voltage. So light trapping not just increases the current, also increases the voltage. And the voltage increase is recognizing the free energy of any resource depends upon how concentrated it is. I'm claiming that if you take a jagged piece of glass, the internal light intensity will be 4n squared times higher versus a plain parallel sheet of glass. And that additional concentration represents free energy. So that I'm projecting then that there will be a voltage boost of KT log of 4n squared, which is actually a big voltage boost. It's about 1/10 of a volt at the operating point. So it has led to some of the new records over the years. Now, so it's very, very advantageous to put some geometrical texture on the solar cells. However, people come to me and they say, total internal reflection, isn't that at odds with what you're trying to have as an anti-reflection coating to let the sun in? So don't those two words mean the opposite? And yes, seemingly the English language is a little clumsy here. It seems like those are opposites. But I remind you that the total internal reflection is not changed at all by an anti-reflection coating. Total internal reflection depends upon the overall index difference between the interior of the solar cell and the exterior. And the anti-reflection coating only applies to that small number of optical rays that are actually able to go into the escape cone. And so don't be upset. A good solar cell has to have both total internal reflection and an anti-reflection coating. They're not opposites. So one of the things I proved when I derived this about 30 years ago, I proved that just by statistical mechanics, there is no geometry better than a random geometry. Now, this has upset people over the years. Many people have come up with specific geometries, said it's got to be better than a random geometry. And they come to me, and well, the first time I ran into this was when I was working at Exxon, and I had done this, and then some other scientists at Exxon said, well, that's good, but we can do better if we have an actual grading type structure or some periodic structure. And I was pretty mad at them because they not only were they taking my idea, but they were messing it up with scientific falsehoods, because you don't want that. So I was wondering, what could I say to express that this is the wrong avenue? So I said the worst thing you can say in an energy company, that if you do this, you will defy statistical mechanics. If you really think you can beat the 4n squared factor, you will defy statistical mechanics, and therefore you will end up making a perpetual motion machine. Now, this is the worst insult in an energy company, the absolute worst insult. And they said, no, of course, we're not going to make a perpetual motion machine. So, nonetheless, people have come back to me and said, surely there must be a way to beat the 4n squared factor. And to this day, papers are published trying to beat it. And it might be possible. People ask me, a photonic crystal, surely that might do better than a random surface. And I used to say no. But actually, I've reconsidered, and in the case of very, very thin films, less than a wavelength thick, there might be a role for photonic crystals. So let me show you a little calculation. This is math, but it's kind of interesting math. If we have let's say, gallium arsenide solar cell, sometimes they're pretty thick. You want to absorb all the light. Maybe they're 3 microns thick. But if you accept this 4n squared factor, that would allow the gallium arsenide to be only 60 nanometers thin. So the question arises, how can you make a film that is incredibly thin, would cost much less because there's less material, and nonetheless you want it to absorb the same amount of light as the thicker material. And so the question is then, what kind of texture should you put on it? And when it's less than a wavelength thick, my prescription of going random doesn't mean anything. How can you talk about randomness if it's only a fraction of a wavelength thick? So you have to have some actual pattern. And so we're actually trying to solve mathematically what surface texture on a thin film will cause that thin film to absorb the greatest amount of light. And now a lot of people are saying, well, we're going to beat 4n squared. But even to approach 4n squared in this limit would be a great accomplishment, because it's already thin enough. You don't need to make a solar cell any thinner than 60 nanometers. In fact, it doesn't have to be that thin at all. So we just need to do the best we can. We may not even reach 4n squared. So we're trying to solve this by a mathematical technique which we call inverse design, where we have a surface and we move the surface around, and we try to adjust it so that it gives you the maximum optical absorption. Here's an example where, relative to single pass, the absorption is enhanced by a factor of 25. But a little bit wavelength dependent, but still a strong enhancement factor. And so this gives you an idea of the figure of merit we're looking for, and some of the geometries. This would be a starting geometry. We have found some unusual thing. There seems to be, in this mathematical problem, some spontaneous symmetry breaking. The thin film will absorb the most light when the surface texture is somewhat asymmetrical. In this case, it's elongated, which is very puzzling. When my student first got this, I said, this is asymmetrical. You expect me to get in front of a big audience and tell them it's asymmetrical, and we don't know why it's asymmetrical? So we don't quite know why. We have some ideas having to do with the phase space and the coupling of different modes, but it looks very much like spontaneous symmetry breaking is part of this optimization. If we go further, these ovals become more kidney-shaped. So it is nature trying to access more of the internal phase space. That's my interpretation now. Okay, I've said as much about current as I want to say. We've done fill factor and we've done current. Once we do voltage, we're done. We understand the solar cell. Now, voltage is rather more difficult to understand. Not too many people understand what determines the voltage, but I will show you how to derive it at home. Okay, and now I will concentrate on the open circuit voltage. And now, of course, with the fill factor, you have to give up a little voltage. You can't get the full voltage. But if you give it up, you can do a little calculation. You give up a few kT, it's due to statistical mechanics. Don't worry about it. And if you can just get the highest open circuit voltage, you'll also have the highest operating voltage. So that's the question. How do we get the highest open circuit voltage? So I will show you how to calculate this. It's actually not so hard to calculate. However, you have to believe in something. So you have to believe in the Boltzmann factor. Now, if you've taken freshman chemistry, they tell you about the Boltzmann factor right away. And you're supposed to accept that. So if you have accepted the Boltzmann factor as being a ratio of probabilities, then you can derive the voltage. Okay? So here I have the Boltzmann factor, and on the right I have a ratio of probabilities. Now what are the two probabilities? Well, it's a probability of being in the excited state with the sunlight on, but even in pitch darkness, you still have a small probability of being in the excited state. So that ratio of probabilities is representing a free energy, and that's just it. It's just it appears that energy appears in the exponent, and it's just like a normal Boltzmann factor. Okay, and indeed this works. You take the logarithm of both sides, so this exponential turns into the free energy. The free energy is really just the voltage, and then I bring the I do a natural log of the probability ratio. I have a natural log here, and I have this kT. This kT carries over to the right-hand side. And that's it. That is the formula for calculating the expected voltage of a solar cell. It's the ratio of excited state population in the light versus the dark. If you know that ratio, you're in good shape. I should mention that when I first was learning this subject, I was at Exxon, and we had a consultant at Exxon, Bob Schrieffer, who was a Nobel laureate, and he was consulting with him about hydrocarbons. And but they were paying him very, very well to be a consultant. I was just a worker. They were paying him very, very well. So he had to put up with things. So one of the things he had to put up with is management reviews. And and we both sat in the back row, and I was bored stiff, and he was bored stiff. And I had noticed that in a semiconductor, this voltage formula works, but there's a factor of 2 here. However, if you do it for molecules or quantum dots, there's no factor 2. And I was puzzled by this. And I leaned over to Bob, and I said, Bob, why is there this factor of 2 difference here? This is not his field, you have to remember. And he thought about it for about 15 seconds, and he says, you have twice as much phase space. The electrons fill the phase space, and the holes fill the phase space. Whereas in a molecule, the electron and hole are sitting right on top of each other. And so you only have one phase space to fill. And that's the factor. It's the correct explanation. What I found amazing about this is that with no warning, he answered a very hard physical question. To me, it was hard. He answered it correctly and with 15 seconds of thought, which is very, very impressive. Okay, so there's that factor 2. But let's just look at the molecular case or the quantum dot. So we have this ratio. Now, the excited state molecules can emit, so you'll see some external emission. And also in the darkness, in the pitch darkness, you'll still get a little bit of thermal emission. So this is the same as the ratio of population. So this open circuit voltage is the same as the ratio of the light emission from the material in sunlight versus the light emission in the dark. And so Shockley took another step. He said, look, the ideal solar cell, the photons come in, they excite electron-hole pairs. Ideally, you don't lose them, so the only thing they can do is recombine and throw the photons right back at the sun. And he said that would be the ideal situation. And so if that's the case, the external luminescent emission for the ideal case would actually be equal to the incoming sunlight. Every photon of sunlight coming in, there's a luminescent photon coming out. That's the most ideal condition. There's no non-radiated recombination. You're not losing light anywhere. It's very, very ideal. And indeed, in 1961, Shockley derived this formula. And it is like the most important formula in this field because it tells you what voltage to expect. And it's very important for us because the luminescent emission, so I'm supposed to actually tell you how we broke the record. And the record has been broken by a big margin. And part of it was understanding the optics of this luminescent emission. But you can just take it from the excited state population in the light, excited state population in the dark, or light emission in the light versus light emission in the dark, or incoming sunlight versus band-to-band emission in the dark. Any of those will give you the correct voltage. Okay. However, there's an even easier way to get the voltage. And the easier way of getting the voltage is to recognize that photons have entropy. Whoops. Photons having entropy. How can that be? Yes, they do. I'll show you exactly how to calculate the entropy of a photon. Now, you might say, you know the energy of a photon. It's h nu. Planck told us that. But what if I asked you the free energy of a photon? Well, then you have to make allowance that the photon might be carrying some entropy. And if you follow statistical mechanics, the entropy is related to how many configurations the photon can possibly be in. And that's all these configurations give you the entropy. And this is another way of getting the voltage, because the voltage would be the photon energy minus all of these entropy terms, and that gives you the free energy, and the free energy is the voltage. Okay? So you might say, how will I ever possibly calculate the entropy of light? I think probably that hasn't come up too often in this auditorium. Okay? But there's a very simple way to address that. And it's as follows. If you look at sunlight, the rays of sun, you might say, well, they're coming directly from the sun. And yes, you know that they're coming directly from the sun. But when you make a solar cell, you'd prefer to make a solar cell that captures all the light coming from all angles in the sky. So that means the solar cell is throwing away information that you knew. You knew where the sun was in the sky, but the solar cell prefers to throw that information away and accept photons from every angle in the sky. So the biggest contribution to the entropy of sunlight is the angle randomization versus where you knew it was a small angle, it was about half a degree in the sky where the sun was. Yet you throw that information away and you're accepting from all 4 pi's to radians. Now that ratio of the solid angle subtended by the sun over the whole solid angle, let's say in a Lambertian, the solid angle is pi's to radians. That ratio is the entropy. And it's a number of different configurations. You had a certain configuration, you threw the information away. So you had all those angles. So the number of angles is pi over the solid angle subtended by the sun. That number is approximately 30,000. So the sun occupies only 1/30,000th of the sky. You've thrown that information away. That's entropy. And so you lose kT log of 30,000. Well, log of 30,000 is about 12. So immediately you lose 12 kT. So if anybody wants to know what is the main entropy of sunlight, it's the angle randomization entropy. And the correct answer in entropy units is 12K, because the natural log of 30,000 is 12 times K. That's it. The entropy of sunlight is almost completely dominated by this one term. And that immediately causes you to have an output voltage that is 0.3 of a volt below the band gap. Now, when I first heard about this, so the angle subtended by the sun in the sky, that's astrophysics. Astronomy. What does astronomy have to do with solid-state physics? Okay, but it does, because we have to ask, well, what is the resource? The resource you're using is the sun in the sky, and you have to know some facts about it. Okay, now, so we've immediately given up 0.3 of a volt. Now, there are still many solar cells made that do not take advantage of the light trapping. And so you lose, and that's would have concentrated the light. You can think of it as when the light refracts into the semiconductor, that it refracts to a tighter angle, and the sun looks even narrower. So it's the same effect. And if you don't take advantage of it, you lose another natural log of 4n squared. That's another 0.1 of a volt. Now, I mentioned you have to give the electrons and holes a reason to go into the wire, so we have to go down to the operating point and give up a little bit of voltage. The little bit of voltage you give up is a few kT. The actual number is this. So this is numbers around 4 kT. So to get to the optimum power point, you give up another tenth of a volt. Keep losing things. Okay, all these are entropy terms. Then we have something that's eminently avoidable. And this eminently avoidable term is due to the fact that most materials do not luminesce well. And if you have inefficient luminescence, it is tantamount to thermalizing the energy, which means you have more entropy. People make solar cells with an external luminescence of 10 to the minus 5. I've been fighting against this for 30 years. People still make very inefficient solar cells that way. If you are foolish enough to use such a material, which includes where most of the investment has gone, which is copper indium gallium diselenide, cadmium telluride, the darling of Wall Street, and you lose another 0.3 of a volt. Okay, and this way of dividing up the free energy was actually done by a graduate student at Berkeley who was studying photosynthesis. He was studying the leaf, and he was working for Melvin Calvin, and he went beyond Shockley's derivation, broke it up into all these free energy terms, which really expose what's going on. And I hope you find this as helpful as I have found it, that it's not a mystery where the free energy is lost, and the dominant loss is very easy to understand. The dominant entropy is due to the random directions of the photons in the sky, when you knew they originally had to come from the sun. Now, if you add up all these losses, well, it's pretty bad. It's 0.3. Let's add them all up, and pretty soon they add up to 0.8 of a volt. So let's say you start with silicon, which is a 1.1 volt band gap, and all those entropy terms cost you 0.8 of a volt. So by the time you're done, from all those gigantic photons, you could end up with only 0.3 of a volt output. And this actually happens sometimes. And so I would say it's best not to have all these terms. The term that we can actually influence, we can choose a material that follows Shockley's prescription. Luminesce well. Do a really good job with luminescence. So what has happened over the past 2 years is that the solar cell efficiency record has jumped, and it was stuck at 25.1% for 17 years. And in the past 2 years, it has suddenly jumped up. And this is because of a recognition of the new physics in solar cells. So the new physics almost entirely involves the boost in voltage. In other words, that efficiency boost came with the same current, but with a better understanding of the voltage. So I'd like to share the physics with you. It's very interesting, I think you'll find. And here's the assertion I'm going to make. We had solar cells. They were stuck for almost 2 decades at 25% efficiency. And they were normal solar cells. Now we have some new physics, and we can make up the gap, because the Shockley limit was 33.5%. We were stuck at 25%. We were missing some of the physics. And now we've included the new physics, and now we have efficiencies well in to where we're starting to approach the real Shockley limit. So it was a riddle or puzzle. Why were we still 8% short? And I'll show you why. It has to do with optics. So Shockley said that any absorber also has to emit light. The solar radiation comes in. It's very difficult emitting the light. Light is trapped internally. It bounces and bounces, suffers parasitic losses, gets reabsorbed, suffers losses because the emission efficiency is not 100%, bounces, finally gets absorbed, re-emitted, and has a chance of getting out. Now, according to Shockley, ideally, every incoming solar photon would get out. But the problem is it's really hard to get them out. And why is it hard? Because the escape cone is so narrow. 98% of the photons get trapped and have difficulty getting out. So it's very, very hard to do. And now I will introduce this equation. You won't find this in Shockley's paper. But you will find this in the paper that I mentioned from the 1960s, where this graduate student had broken up the entropy into a series of terms. And what it says is that, yes, you'll have the ideal voltage, but only to the extent that you have perfect re-emission of the solar photons. And to the extent that you fall short, that you fail to externally fluoresce the incoming solar photons, that you will lose voltage by this amount. And if it's like really bad, like 10 minus 5, you will lose a lot of voltage. It's a lot of solar cells are like that. I don't like that. But it says if you really want to achieve the theoretical limit, you must have a solar cell that does a great job emitting light. However, this is extremely paradoxical. Why should a solar cell emit any light at all? Yet it is a requirement for achieving the highest efficiency. So there's a paradox there. So what is this new physics? And it's sort of explained on this slide. The old picture of a solar cell, up until recently, was the light comes in, produces electrons and holes, and the electrons and holes get collected. Okay. On the other hand, in the new picture of a solar cell, the light comes in, produces luminescence, the luminescence is trapped, it bounces around, can't get out, gets reabsorbed many times, reabsorbed, finally it gets out. That in one sun, in this new concept of solar cells, in one sun, there could easily be 30 to 40 suns of infrared luminescence bouncing around inside a one sun solar cell. And that is a prerequisite for achieving the theoretical efficiency limits. And so it's this recognition, going from this simple picture of a solar cell, which is in all the textbooks, to this more nuanced description of a solar cell, where the solar cell has to manage the external luminescence. And indeed, it fills with internal infrared luminescence. And only when it fills with infrared internal luminescence does it have a hope of achieving the highest possible voltages. And this is what has happened in the past couple of years. But it's very, very hard to do that, to trap and then re-emit that internal luminescence. Because of all the bouncing, the reflectors have to be very good. The reabsorbers have to be very good. It has to be a material that has 99% luminescence efficiency. Indeed, you may need 99% luminescence efficiency just to get 50% out because of all the bouncing and all the reabsorption. There could be 50 reabsorption events. So it's very, very challenging. Now, so I prefer to think of the solar cell as just requiring excellent light emission. But people like a more traditional picture. This is a more traditional picture. This says, oh, the recycled photons are not lost. They get reabsorbed. And since they're reabsorbed, they produce more carriers. The effective carrier lifetime increases. If the effective carrier lifetime increases for a fixed amount of sunlight, that increases the carrier density. Any resource that is more dense has more free energy. Therefore, that leads to higher open circuit voltage. Yes, all that is true, but the more universal truth, in my view, is that the solar cell has to emit light and has to emit light efficiently. But it's very, very hard to do because it does require, because of all the many photon recycling events, you need tremendous internal quantum efficiency. And if you do a calculation, here's on the reflector, the cell efficiency, it rises and rises as you make the reflector better, but most of the benefit is in the last 5%. Over 95% is where you get a good portion of the benefit. 90% rear reflectivity is not enough. And the same thing with efficiency in terms of internal fluorescence yield. That's not the reflector. This is just the internal luminescence yield. Now, fortunately, gallium arsenide is unique among all materials. I believe it has the highest luminescence yield of any substance, well over 99%. So we have a chance of being way up there and getting these very high efficiencies. But really the benefit occurs after 95%. And this sort of shows that you get a certain benefit from going from 80 to 90, but going from 90 to 100% there's a much bigger boost in performance. So what has happened with the records? The records have gone up, and the record solar cell is now 28.8%. The previous record was 25.1. It's been almost entirely due to voltage. The previous record voltage was 1.03, and now the new record voltage is 1.12. So it's all about the voltage. The current is practically unchanged. By the way, nobody today claims records based upon their good faith. If you want to claim a record, you have to send your solar cell to NREL, and they check it, and they tell you you have a record. So this is indeed the record that they have declared. Okay, so this is a third party checks that out. And this is the new physical principle on which it is based. But it requires tremendous fluorescence yield, well over 90%. And it says that the one way to think of it, and my preferred way of thinking of it, is that why do you need luminescence? And if you look at this formula that I showed you before, that this was measuring the excited state population. The external luminescent emission was measuring the excited state population. The excited state population through the Boltzmann factor gave you the voltage. So the external luminescence, in my viewpoint, is actually a voltmeter into the cell. And therefore, why should you have good luminescence? Because that says it's tautological. It's the same as saying you want a high voltage. So let me summarize. For solar cells, once they reach 25% efficiency, don't worry about the electrons and holes. The electrons and holes are doing fine. Any improvement above 25% efficiency has nothing to do with electronics, has everything to do with optics. And so all of the records above 25% were about photon management internally in the cell, in particular managing the photons to be externally emitted, which requires low parasitic losses, etc. And this leads to a mantra. And the mantra is a good solar cell has to be a good LED. Okay? But it's counterintuitive. People are upset with this. Why should the solar cell emit any light at all? It's counterintuitive. It's supposed to be absorbing light. So this is the paradox. So let me try to settle the paradox for you, because I think that is the whole paradox of this field. Well, why is it good to have good external luminescence? Well, if you have good external luminescence, it means that the non-radiative losses were low. So that's good. It's a good thing to have. So the good external luminescence tells you have a low internal losses, and therefore it's got to be good. Okay? And for sure, non-radiative recombination would be bad. So that's one reason why external luminescence is good. To get rid of, it shows that you have low non-radiative recombination. Second reason why external luminescence is good. I indicated before. The good external luminescence means that the photons are being recaptured, being re-emitted, and the recapturing means that the lifetime increases and so forth. So that's another reason. Third reason why external luminescence is good, and that luminescence is voltage. That's my belief. Indeed, luminescence is often used as a voltmeter, and this is how they do it. They have a solar panel array, and they take an infrared photograph of, believe me, the solar panels, when they're working right, they actually emit some light. And so they look at the emission, and if there's part of the panel that doesn't show up, that's not emitting light, they know that part of the panel is bad. Okay, they actually use this in manufacturing as a tool. Luminescence is voltage. Okay, if you doubt that, you have the NP product, you have this law of mass action in semiconductors, the connection between luminescence and voltage. So I say it's obvious why. We have to have luminescence. And by the way, don't be afraid that you're losing that much. Under ideal optimization, you lose about 2% of the light. It's like charity. Although I hope you give more than 2% to charity. But the solar cell works best when it takes in 90% of the light, delivers it as current, and takes 2% of the light and gives it back as luminescence. That's actually the optimal point of operation. So I told you before, you don't want to go to an extreme or another. You don't want to try to capture every bit of current. And it's part of that optimization. And that's the amount of light you have to give up. And it is indeed used as a quality control metric in manufacturing. So this viewpoint is tautological. Good luminescence is good voltage. And so it falls back to this formula. And it is indeed the external luminescence that matters. It is often difficult to get the light out. Now, I have a lot of objections to this idea. So people say, well, my solar cell doesn't luminesce at all. They're working on some kind of solar. It doesn't luminesce at all. And I say, well, that's probably not correct. Undoubtedly, it's not a very good solar cell. The voltage is very low, but there's always some tiny amount of luminescence. So that's how I would answer that objection. Another objection is, I need to separate the electron hole as quickly as possible, so they don't have an opportunity to have non-radiative recombination. And my answer to that is, if you have the type of solar cell that requires that built-in electric field, that built-in electric field is voltage that's not going to be available to you. So this is not a good thing. It may be necessary, but it's not a good thing for your solar cell. Third objection. I need to suppress fluorescence because the electron hole will recombine before I have a chance to get the electricity out. And the suppressed, and I say, on the contrary, the fluorescence is good. The suppressed fluorescence is an indicator that voltage was sacrificed for current, and the carrier extraction efficiency needs to be improved. So yes, the potential is there for high voltage, but the rest of the cell is not working well. So these are the objections I've had to deal with. Now, I'm going to skip this. This is just saying that we can make more efficient solar cells by having a dual junction. I think I'll skip this part. And I'll just finish with the sociological survey. So everyone agrees that gallium arsenide are these are the most efficient solar cells. Where cost is no object in space, they use gallium arsenide solar cells. But they don't have to cost much. And I am the founder of a company called Alta Devices that has taken the cost out of the gallium arsenide solar cell. This was a website about 18 months ago saying, oh my God, they're raising a lot of money, but they're very secretive. By the way, I was against the secrecy, but I was overruled by the other board members. I thought we should be telling our story. So I'm happy now to be telling the story. Now, the key to making the gallium arsenide inexpensive is the expense is coming from the very expensive gallium arsenide substrate. And the key then is to reuse the substrate to peel the solar cell. The solar cell is a very thin film on the substrate. It doesn't have to cost much. You peel it off, and then you reuse the substrate many, many times. The acid comes in and floats the epitaxial film off. Epitaxial film, this is the best gallium arsenide you're ever going to have. And it can be made in low cost because you're reusing the substrate. Now, it just so happens I have some with me. And I see there are too many people here to pass it around. But if you come up afterward, I'll be happy to show it to you. Now I have to find it in here. You see, this is a little bit unrehearsed, but find it. Okay, here it is. Okay, so these are the actual solar cells that broke the world's record, and that also project out to be very, very low in cost. We peel them from a 6-inch wafer, and this is exactly how it comes out. This is epi single crystal gallium arsenide of the highest quality. It is peeled from the substrate. The peeling process has finally been perfected by Alta, and it peels very, very quickly. The acid just goes in, and then you grab it with a vacuum chuck and pull it off. Okay, and although this is an inorganic single crystal thin film, it is totally flexible. Okay, and it is also the world's record solar cell. Now, ask what told us that we were going to break the record. The key step was getting the film off the substrate, because substrate quality is never as good as epi film quality. So as long as the solar cell was sitting on the substrate, you could never get the photon recycling and the photon re-emission, because the photons would just disappear into the substrate. And so the instant we peeled the solar cell off the substrate, the voltage immediately started going up. And then I looked back at the theory we had done, and the theory had already anticipated it. Okay, and so that's the key thing. And so I have this to show you, and I have a similar one here. And come up afterward to see these. There's a similar one here. And by the way, you know, these are made in huge volumes. I mean, this is one where you've cut it up into smaller pieces to make a panel. This leads to a lot of cleverness in panel design, because you see that the individual cells are staggered. So if one cell is bad, the current finds a path around that cell. And so we actually have machines that make this. And you can imagine that this is actually a more scientific panel. And so this is the process I just showed you. However, this is an old result, 2-inch. I'm showing you 6-inch. The idea is you put a droplet of acid in, and the aluminum arsenide layer that is attacked by the acid, that could be as little as 2 nanometers thick, and still the acid will go all the way across. That's amazing.
It doesn't react with the
No, there's an amazing coincidence in nature. If you have more than 40% aluminum in the algas alloy, it is attacked by the acid. If you have less than 40%, it is not attacked. And the selectivity is at least 100 million to 1. And this has not been explained theoretically. We can speculate, but it has never been explained. But it harks back to the Handbook of Chemistry and Physics. There is you look at the inorganic compounds. There's a column that says IS, IS, IS. Does anyone remember what that is? It has to be the old timers. Young people don't have to use a hard copy like that. The IS was which inorganic compounds were soluble, which were insoluble. And it's binary. Nobody has explained that. We're taking advantage of that. For some reason, it's binary. It's either soluble or insoluble. In algas, that happens at 40% aluminum. And that's the basis of this epitaxial liftoff process. So it leads to very low cost mass production, and then you reuse the substrates over and over again, and you make record cells, etc. But this lesson has not been lost on the silicon world. So we are competing with the silicon world, which is a dangerous place to be. And I've been telling them for years, you ought to peel the films. So they are now peeling the silicon. And the way they're peeling it is they put on electroplated nickel and then a plastic handle, and then they yank up on the plastic handle, and the silicon cracks. But it cracks in a very controlled manner. It cracks all the way across like this, and they end up peeling the film. Now, the reason why it cracks like this is that the part of the silicon adjacent to the nickel is under compression. When you electroplate, you can actually put compression on the film. When there's compression on it, it's stronger, so it doesn't break. So immediately adjacent to the nickel, it doesn't break, and the rest of it just peels across. And this was done at IBM. There was some similar work done in Austin, Texas, a startup in Austin, Texas, and they had a different name. They called it exfoliation, but it's the same idea. And they would peel the silicon. Usually get films about 25 microns thick, which is very good for silicon. Now they have other methods of peeling. This one, the company's not telling, but they have a way of peeling, and I think I have an idea how they're doing it. But it shows that they have finally realized you cannot use thick substrates because it's simply going to cost too much. You've got to peel the film at the thickness that you're actually going to use. Today, the solar cells are not peeled. They're cut with a saw. They cannot make the saw blade any thicker than about 200-300 microns, and they waste all that sawdust is high purity silicon, so it's wasted. And this is another picture of these Alta cells that I was just showing you. Okay, so what is the status of the industry? So I'll give a technological status, then maybe the economic status. The crystal silicon is still king, over 90% market share. The poor silicon plants struggle to reach 15%, but the best silicon plants are reaching 23%. Then you have this compound, which is sometimes shortened into SIGs. In Silicon Valley alone, 7 years ago, 20 different SIGs companies were started. Okay, one of them was Solyndra, but there were 19 others. They are basically all being shut down now. It's just not competitive with silicon, and you see their efficiency wasn't quite there, and the silicon also has its cost reduction. On the other hand, you have First Solar. This is the darling of Wall Street. Has the highest market capitalization. They're the only ones who are making cadmium telluride solar cells, but the efficiency is not great. Obviously, Wall Street disagrees with me. I think this company is in trouble. Okay. Then we have flat plate. Now, flat plate doesn't mean that it's a plate that's flexible, as you can see, but what it means is that it's not a concentrator, and so it accepts all the rays of the sun, and the record that I showed you was 28.8%. And then you have concentrators that look very good, higher efficiency, above 40%, but that 40% only applies to the direct rays of the sun. If you multiply by 0.7 to allow for the fact that only 70% of the sun's rays are direct, it ends up, it's pretty similar efficiency to the flat plate I showed you. So that's the status of the industry. The biggest thing that has happened, however, in the past year is that the Chinese production subsidies, they have built, with low interest loans or no interest loans, they have built a gigantic capacity. They have in China 60 gigawatts a year of production capacity. And the world demand today is 30 gigawatts, and does not appear that it's going to get much larger than that right away. So there's a tremendous amount of low efficiency capacity in China, and this is driving down the prices. So where we needed to wait for technical progress to get low prices, we're getting low prices now because of this exorbitant subsidy. So it's creating a mess of the industry for all the other companies. But on the other hand, the cost we were supposed to achieve 10 years from now, we're getting that cost today because of those Chinese production subsidies. So stay tuned. The industry will evolve further. It's been an up and down roller coaster. And thank you for your attention.
A little bit of time for a couple of questions from this big audience. Ray?